All right, greetings 215 students. I apologize that this has to be done this way. I thank you all for your patience. We're outside of Cincinnati, I think, right now. So I'm going to go through this quickly. You may need to pause the video to write down the definitions and stuff. But yeah, pause it as needed. So, and part of the reason why we can do this pretty quickly is because we've done hypothesis testing before back in chapter 2. So now we're going to do a hypothesis test for the population mean. So it's the same 5 steps as we had back in chapter 2. Step 1, assumptions and conditions. Step 2, formulate your hypotheses. Step 3, calculate your test statistic. Step 4, find your p-value. And step 5, report your conclusion. So step 1. The assumptions and conditions are the exact same as what they were for a confidence interval. So we need a random sample, or at least a sample that avoids bias. And then for means, our magic number is 30. If the data is normal, doesn't matter what your sample size is. If the data is not normal, we need a sample size of at least 30. Step 2, formulate your hypotheses. Our null hypothesis will always be of the form mu equals mu naught. So back in chapter 2, we said stuff like p equals 0.5 or p equals 0.1 for our null hypothesis. Here we'll say something like the average height of all Grand Valley students is equal to 67 inches. Or the average number of Facebook friends for all adult Americans is 1,000. Where we say our parameter of interest equals some null value. Our alternative hypothesis, just like back in chapter 2, we have 3 options. We can either use not equals, less than, or greater than. So the average height of all Grand Valley students is not 67 inches, or it's less than 67 inches, or it's greater than 67 inches. And then if this is your alternative hypothesis, you may also choose to use mu is greater than or equal to mu naught as your null. If this is your alternative hypothesis, you may choose to use mu is less than or equal to mu naught as your null. But just like in chapter 2, when I'm doing it in class, I always like to use the equal sign for my null hypothesis. Step 3, calculate your test statistic. The overall formula for our test statistic is the absolute value, our sample estimate, minus our null value, divided by our null standard error. So our sample estimate is not changed from a confidence interval. Our sample estimate for mu is x bar. Our best guess for the population mean, if we only have sample data, is our sample mean. Our null value is mu naught. It's what we used in our hypotheses. And then the nice thing about means is the null standard error is the exact same as the standard error that we used in our confidence interval. And the reason why that is because there's nothing gained by assuming that the null hypothesis is true. Sure, we can assume that mu equals mu naught. That does not change anything in our standard error formula. Back in chapter 2, when we had to assume that p equaled p naught, that did change our standard error. Here it does not. So the standard error for our hypothesis test is the exact same as the standard error that we use for our confidence interval. Step 4, find your p-value. Because we're dealing with means, we have a t-distribution working in the background, not our standard normal z-distribution. So we do have to find degrees of freedom. There is another table called two-tailed p-value for the t-test statistic. And then you'll notice up here at the top, we've got a bunch of numbers. These are all the possible degrees of freedom that we will use. So there's actually 3 pages to this one. And of course, my computer's being buggy. So 1 through 11 degrees of freedom, which, to be honest, we're not going to use that a whole lot because typically we'll have more than 11 degrees of freedom. 12 through 22, and then the one that we will use most often is the 3rd page, where we have a bunch of different degrees of freedoms. So you'll notice that there's a big spread between the degrees of freedoms, but all of our p-values are really, really close between the columns. So just like Chapter 2, and in fact, we can use the old table that we used in Chapter 2 as well. I'll explain in class how we can do that. But just like in Chapter 2, these are two-tailed p-values. So if you only want one tail, divide by 2.
Grandma does have Wi-Fi.
And then step 5, report your conclusion. And this is always going to be the same. If your p-value is less than 0.05, we reject the null and accept the alternative. If the p-value is greater than or equal to 0.05, we fail to reject the null and fail to accept the alternative. We're going to go back to use the data that we used in the previous section. So it dealt with the ideal number of children for a family to have according to 1,097 female responders. The sample mean was 3.16. The sample standard deviation was 1.91. I want to perform a hypothesis test to determine if the population mean among all women for ideal number of children is different than 3.25 children. Your notes say 3.5. I'm going to change that to 3.25, so you might need to squeeze it in there, cross out, and put 3.25. So let's quickly run this hypothesis test. So are the assumptions and conditions met? Yes, and we know that because they were met for a confidence interval. Although I don't know if we talked about it for a confidence interval. But we have a random sample, or at least as far as we can tell, this is a good random sample. The General Social Survey generally does a pretty good job of that. And we have well over 30 people in our sample, so it doesn't matter if the data is normal. So yes, our conditions are met. Our null hypothesis, mu equals 3.25, because what we're trying to prove, our alternative hypothesis, is that it's not equal to 3.25. So here we do have an example of a two-tailed alternative hypothesis. I don't care if it's less than, I don't care if it's greater than, I just care that it's different than 3.25. And because we are open to both sides as being acceptant of the alternative hypothesis, this becomes a two-tailed p-value. Our test statistic, we have the absolute value of our sample estimate, which is 3.16, minus our null value, which is 3.25, divided by our null standard error. But we've already calculated this number. We did this earlier this week because the standard error is the same from a confidence interval to a hypothesis test. So I think the different classes got a little bit different value here, but rounded to the nearest 10,000th, it's 0.0577. So the top is 0.09. So we have 0.09 divided by 0.0577. So our test statistic, and this is called a t-statistic because this whole thing is called a t-test. A hypothesis test on proportions is called a z-test. A hypothesis test on means is called a t-test because we're using the t-distribution. So we have a test statistic of 1.56. So we can go to our table. 1.56 is not on here. We round down to 1.55. We go all the way over because we are going to use 1,000 degrees of freedom because we have 1,096 degrees of freedom. That's not on this table. So we round down to 1,000. And our p-value, our two-tailed p-value is 0.121. We are not going to divide this by 2 because we want our two-tailed p-value. So our p-value is just 0.121. This is greater than 0.05, so our conclusion is we fail to reject the null, we fail to accept the alternative. There's not enough evidence to say that mu is different than 3.25. Again, cannot stress enough, we're not saying that it is equal to 3.25 because we never, ever, 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 ever accept the null hypothesis. We just don't have enough evidence to prove that it's different than 3.25. So last class period, we came up with our confidence interval, and we stated that we were 95% confident that the population mean was between 3.05 and 3.27 children. Does this conclusion match up with our conclusion from our confidence interval? So does our conclusion that we just came up with in our hypothesis test, does this mesh with what we found on Monday and Tuesday this week? So, a little bit of extra pause. I want to encourage you to pause the video and try to answer this question before I give you the answer. That should be long enough. If I got some peanut gallery comments. I'm almost done. Okay. All right. I totally lost my train of thought. Everyone say hi to my wife.
Hi.
There's Kelly and there's Chad. All right. I'm almost done, guys. We can leave really soon. So these two conclusions do match up. Because 3.25 is in our confidence interval, what we're saying is, sure, mu could equal 3.25. It's inside the range of values where we say we're 95% confident it's in here. So sure, mu could equal 3.25. Our conclusion for our hypothesis test, sure, it could equal 3.25 because we don't have enough evidence to say that it's different than 3.25. So yes, both of these conclusions match up, and we are good to go there. Prior to class on Monday or Tuesday, I want you guys to try these graphs out. We haven't done a whole lot with these graphs, but I want you to give it an honest effort before class on Tuesday. Don't forget to change these to 3.25. And then try to answer this question as well. I will give you a hint. This is very similar to one of the exam questions from exam 1. If you have any questions, you can email me over the weekend. I will try my best to get to those as quickly as possible. Otherwise, hopefully we can head off any confusion on Monday or Tuesday. And for those of you that were not in class this past Monday or Tuesday, remember to come wearing your costume. And I will see all of you guys then.